Hello and welcome. I am Dr. Joel Rosenfeld, and this is my numerical analysis class. So, today what we're going to be talking about is just really what this class is about. I'm teaching numerical analysis as an undergrad level, senior level course in mathematics. And I'm also going to be teaching a tomography course, and both these, if you follow my YouTube channel, both these are going to be posted, both lectures for these classes are going to be posted up here, and you can follow along if you'd like. In any case, so we should talk about what numerical analysis is, who I am, and we'll do a few simple historical examples here today. So I guess start with me, then we can get to course content. So I'm Joel Rosenfeld. I got my PhD back in 2013 in pure mathematics. I was studying operator theory and functional analysis, specifically in reproducing kernel Hilbert spaces. So these are spaces that ended up being used a lot in things like data science and approximation theory and whatnot. As far as I was concerned, I just saw them as these regions where you can apply operators to, and etc. I had never really given much thought to applications, but then coming up on graduation back in 2013, I found I didn't have a job. I was looking for only research positions in mathematics, and turns out most mathematics positions after you leave slam you with a lot of teaching, and I just didn't want to do that because my goal was to become a professor. So after the job cycle finished in my last year and leading to a lot of panic attacks, I found I had no job. And so then what I did is I started reaching out to engineers. I realized that if I was going to make myself marketable, I have to do what most pure mathematicians don't do, and I had to look into applications. So I went and I tracked down a professor of control theory. I did not realize how big of a person he was in the control theory world until well after I was working with him. But I told him that I would like to learn about control theory. I asked him for references of what I could learn, and then within a few minutes he gave me a job. And so then after that, I worked in engineering departments for about 6 years, in both at the University of Florida and then also at Vanderbilt University up in Tennessee. And this was a combination of working with computer scientists, electrical engineers, and mechanical engineers. What I found working with all these people was that nobody really cared about all my great knowledge in functional analysis. I mean, they cared, they would listen, and if I had something to say that was pertinent to their research, they paid attention. But what I found is that what people were really expecting out of mathematicians was some facility in doing numerical analysis and numerical methods. So I had to do a crash course for myself because I never took a class like this. I had to teach myself how to do quadrature. I had to teach myself how to do polynomial approximation. I had to learn how to use these kernels that I had been playing with throughout my graduate school for approximation theory. And had to learn how to do some basic optimization, things like KKT conditions, gradient descent, things like that. And so over those years, one after another, I basically taught myself how to do all these things that I'm going to be teaching you here today, this semester. So I think it's really valuable for every mathematician, whether you're a pure mathematician or if you're an applied mathematician, to take a class like this at some point, because you don't know what you're going to end up doing when you graduate. You don't know if you're going to stay in academia. You don't know if you're going to go into industry. You might say something now, and you might say that, no, I'll definitely be an academic, etc., but you don't know which way the tide is going to be going. There might not be any positions in academia when you graduate. You might decide that you get sick of it at your master's degree level, and you want to go into industry and actually get a job that pays well. So there's a good chance a lot of you will be asked to do numerical analysis, and even as a professor, it's in pure mathematics. I mean, somebody might come up to you and ask you to do an integral. And well, you better have some method ready at hand so you can do it quickly. So yeah, so basically this class is half of the lessons I've learned, and the other half is going to be just doing numerical analysis. Okay, so now let's talk about what numerical analysis actually is. Basically throughout your time in calculus 1, 2, 3, and differential equations, you've been running into all sorts of different quantities that you express sort of analytically. What that means when I say that is that when you say find a solution to a differential equation, it has a closed form. You can write down the equation and you're done. If you come up to a function you want to take as derivative, you have the chain rule, you have the product rule, you have the quotient rule, and all these nice things that you can employ in order to actually take a derivative. If you want to approximate something, well, you learned in calculus 2 that you can use Taylor series, and so you just spin out a Taylor series approximation, and then you truncate at some point, and then ta-da, that's your approximation. So for instance, e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial, and so you know if you just truncate, then you will actually end up getting a solution. So, and then, for instance, you also learned some root finding in calculus 1. So for instance, if you want to figure out what the square root of 2 was, then you could take the polynomial of x squared minus 2, and make a guess, and then use Newton's method to get at the square root of 2. So you've learned some numerical analysis and some calculus, but now we want to put this all into like one single framework. Most of the time you're not going to be able to actually integrate anything analytically. Using U substitution, integration by parts, and all these other things are really nice, but at the end of the day, it only works on like a handful of equations. Mostly things that are like polynomials times exponentials, or rational functions, and even then we can cook up some that you can't integrate pretty quickly. And as far as differentiation goes, you're not always actually even going to have a function at hand. You might have a collection of, you might have a graph of a function that you've taken a bunch of samples of, and you want to be able to take a derivative of that. Well, I mean, like, if you don't know what the function was to begin with, you can't just use product rule and chain rule. You have to come up with some method of doing it. And then as far as root finding methods, Newton's method is a nice method to go. It actually works out fairly well, and it's the go-to method most of the time. But there's better ones that converge faster, but maybe a little bit harder to code. And so we'll be taking a look at a lot of these things too. So, so the general idea is that we're taking all these ideas they had from calculus, and we're trying to make them quantitative. We want to be able to take derivatives, integrals. We want to be able to approximate functions. We would like to be able to find roots and all these things, and we want to be able to not only come up with an algorithm to do it, but we'd also like to demonstrate that the algorithm, say, converges to what you're looking for, in some fashion, and hopefully in some controllable way. And that's the focus of this course. We're going to come up with algorithms, say for polynomial approximation, and then we'll show that these actually converge as you iterate or take to higher degree polynomials, for instance, to the actual function you're talking about. We would like to take something like the root finding methods of Newton and demonstrate that it converges sometimes, or at least get some ideas of when it converges. And we'd like to be able to get things like convergence rates. It turns out some algorithms might be better than others and converge faster than others, but they might also be harder to code. Or their computation time might be a lot longer than one versus the other. And so we're going to learn how to find this balance as we go, and yeah. Now, as far as textbooks go, as far as what we're going to be studying, I am not using any one textbook for this. I have a whole lot of different resources that I'm going to be pulling from, and the class will be more or less self-contained with the lecture notes and these videos. If you ever want to know something and you want to repeat something, you can always play these videos again, and I'll also post the corresponding notes up there. The format of the class is basically have a face-to-face with me here at the very beginning, then we'll switch to a sort of a whiteboard sort of thing, and then we'll go through and have a mic on an iPad, and we will go through all this, and then we'll have a closeout where you talk to me again, and we'll review the topics we discussed. Let's see, anything else I want to talk about? I guess other important things to mention is grades. How are things going to be graded in this class? As far as the specific grades and how everything's going to fall out, that's going to be on the syllabus. And so, but generally speaking, 90 to 100 is a A- to an A range, and 80 to 90, etc. For B, and so forth. The class is going to have 4 projects and 2 exams. So we'll have an exam in the middle of the semester, and then a final. The exams are put together just so that we don't have to slam you with everything all at once, and but it gives us a good checkpoint to go and make sure that everybody's on the same page. And the projects, we're going to have more or less 4 different units that we're going through here, and each one will culminate in a project where I want you to demonstrate your skills. And so basically the first exam should happen after the first 2 projects, and then the second exam happens after the last 2. I'm not going to make the final exam cumulative, but it'll just correspond to those latter 2 projects. Let's see, anything else I want to talk about? Yeah, so I guess we can go ahead and start talking about some historical examples. So we're not going to dive into anything really complex today, but I did want to give you some sort of hints at some of the things we're going to be looking at, or the types of problems that we care about. So numerical analysis is probably as old as mathematics is. Basically, anytime somebody came up with some method of doing something, they were doing it for a reason, and so they needed to get hard numbers out of it. So one big example of an early numerical analysis idea goes back to Archimedes. Archimedes was a mathematician. I think it was around 350 BC. And he was a mathematician's mathematician. He liked to do things for the sake of mathematics, and he also had this habit of challenging other mathematicians, which was sort of funny. He would so it was a game that he would do where he would like post a result and challenge other mathematicians to come up with a solution to that same result. But he was tricky in that sometimes he would even post a result that was incorrect and laugh at the mathematicians who fell for it, and he would call them out as being bad mathematicians. And so he has a lot of really interesting proofs. He was able to determine the area between a line and a parabola. And he wanted to also do the same with a hyperbola, but he was never able to actually do that, and actually that ended up being a long unsolved problem until we really came around to the idea of calculus. And so, but one thing he did is came up with the first routine for getting approximations of pi, and this was and this gives you the sort of first order approximations that we see today, like say 22/7 or even higher, or more accurate approximations. And he used this and he did this method by trying to approximate the area of a circle. And so I'll talk to you about how to do that. The way we'll prove that it actually works out is not going to be the way he did it, but it's going to be more of the way that we're going to be thinking about problems as we move forward. Other things to talk about, around the same time, we have Heron's formula for computing square roots. It actually works out fairly quickly. You obtain higher and higher precision as you go with iterating this method. So you basically make a guess, and then you maybe guess an over approximate, and then you divide the over approximate. the actual value, which you don't truly know, by the over approximate, and then that gives you something that's going to be smaller, and then you take the average, if I remember right. I will go over it in a minute, and basically each time you use Heron's formula, it actually gets you several decimal places further as far as an approximation of a square root, and so it works fairly well. And it turns out that Heron's formula is actually equivalent to Newton's method, which I described earlier as basically using Newton's method on the polynomial x squared minus 2. So that would give you square root of 2, for instance, in exactly the same way as Heron's formula does. Another thing I'm going to want to talk to you about today is Fermat's method of quadrature. When I say quadrature, I basically mean integration, and he basically came up with one of the first integral formulas in sort of a modern way. So the idea was that he was trying to answer this sort of quadrature method problem with the hyperbola. So basically trying to integrate 1 over x, for instance. We know, by the way, 1 over x integrates to natural log. But, they were just beginning to get to that point where they can talk about that sort of a thing. And so instead of just doing 1 over x, he had decided to approach a problem where he was trying to answer the question of 1 over x to the n, not just 1 over x to the n, but just x to the n where n ranged over a variety of values, integer values. And he came up with a nice method. It doesn't actually work out for 1 over x because that's not actually integrable. But as long as you stick to whole numbers, I think it works out. But he used a combination of geometric series, which we've known about since, say, the Greeks. And then he came up with a nice formula for integrating from 0 to a of x to the n. And then that really, all it really comes down to is using the geometric series formula and also factoring polynomials. And so we can talk about that and just see basically an early quadrature routine, and we'll come up with different approaches when we actually get to that topic. And then finally, I want to talk about something that's actually deprecated. Nobody actually uses it anymore. But it turns out that mathematicians used to really enjoy or really use a lot of tables. So mathematics, before we had calculators, was really hard to do. If you wanted to multiply really big numbers, you were stuck with an algorithm that would take on the order of, say, n squared, where n is the number of digits. And that takes a lot of effort to do, because basically you have to calculate pairwise every sort of product and then come up with a method of adding them together. And so ultimately that's what we call a big O n squared algorithm, and we'll get to what those mean pretty soon. And so mathematicians were motivated to come up with tables of these things so they can just look them up. And in fact, you can exploit the logarithm in order to come at a lot of these problems in a really clever way. So basically, if you want to figure out the product AB, you basically take your table and you look up the logarithm of A and you look up the logarithm of B, and then you take these two logarithms and you add them together. Now we know, as far as logarithms go, if you add two logarithms, it's the same as taking the logarithm of the product, and they knew that too. And so then once you take the sum of these logarithms, you have the logarithm of the product, and then you do a reverse lookup on the table, and then you suddenly have the product A times B just through the reverse lookup on the table. Now this is amazing. So the idea is that you can basically do everything with an order n number of operations, where you basically just have to do addition. And so this reduces the number of operations you have to do by square root, and it makes things a lot faster if you're trying to do these computations. And so that motivated mathematicians to actually use what are called logarithm tables, and every mathematician had them. And I have a book of tables, but they're sort of packed away, and so my wife has some older books that she liked to collect. And so this is the CRC Standard Mathematical Tables. And so really early on in this book, we have like tables of pi and all these other things. But then we have a 4-place logarithm table right in the beginning. And these CRC manuals used to have this all over the place. I don't know if you can still find it anymore. But this is basically what you have. You'd have these, I don't know if it's focusing. There we go, I think it did. So basically you have these tables logarithms. And the idea is that if you want to figure out the logarithm of a particular number, you take its the characteristic and the mantissa and you separate them. And then you look up on this table for the specific value of what you need. And this table just goes on for a long time, and then that gives you the ability to do a lookup and figure out how to do arithmetic with these things. And the tables weren't just reduced to logarithms. So for instance, here's a Barlow's tables, which is fairly popular. Again, one of my wife's books. And here it has, let's see, so it's Barlow's tables, and it covers squares, cubes, square roots, cube roots, and reciprocals of all integers up to 12,500. And so mathematicians were really big on coming up with this. And so some of the earlier tables that were made were by Napier, I'm not sure how to pronounce it. I think he was Scottish, so probably not Napier, I don't know, and Briggs. And they were both roughly around the same time. Napier, I really should figure out how to say that. His method is a little bit more convoluted, and actually we don't really have any good reason, we don't have any good knowledge of his motivation for his methods, although they work. But he used like sort of a physical intuition between developing his logarithms. Briggs actually uses a combination of something like Heron's formula and properties of logarithms by taking successive square roots to get really good approximations. And that man came up with like, I think it was like, he kept an accuracy of up to like 52 decimal points or something like that back in the 1600s. And that is an insane amount of work. We did have decimal and points by then. That came around about the 1400s or so. So we were using sort of the Hindu Arabic number system. So at least we had that. He wasn't doing everything in Roman numerals. That guy did a lot of table production and hand calculations, enough to the point where he actually recognized that if you take the logarithm of 1 plus r for r very small, then that is roughly linear, and he even came up with a proportionality for that linearity, which is basically an early form of finding a derivative. And so that was really interesting. But mathematicians, it's got into such a habit of making these tables that it actually nearly crippled the Manhattan Project. So if you listen to some of Feynman's work, talks on working at the Los Alamos Manhattan Project, he actually was in control of the computer department, or whatever you want to call it back then. It was like these big mechanical machines by IBM. It wasn't digital. We didn't have nice small transistors. These are all mechanical calculators that worked on punch cards. And the reason why he was given this is that the guy who sort of put together the facility, everything started falling apart. He wasn't supervising anybody. Projects weren't getting done. They had a nuclear bomb, and they had to do some calculations to make sure it wasn't, say, going to set fire to the atmosphere. It turns out that the guy who was in charge before him had gotten obsessed with how quickly these machines could crank out a table. And so he was computing tables for arctangent that were highly accurate, and sure, that was fine, but it wasn't important. People have already did that by hand, and we had tables of arctangent. We didn't need new ones. And so the man had just gotten obsessed with like the ability of computers to actually do this really fast, that he sort of lost sight of the fact that we were trying to finish the Manhattan Project. So yeah, I think it's interesting and important to talk about some of these tables and numerical methods or integral into computing all of these tables. And so we'll talk about that briefly today. Anyway, so yeah, so we'll switch over to whiteboard so you get an idea of how these lectures are going to work, and then we'll come back to me in a minute.
So let's go ahead and get started. What we're talking about today is a collection of numerical methods that we've seen throughout history. All right, hold on. Suddenly I can't spell. All right, so we're talking about Archimedes first. And like I said, before, he was a mathematician from ancient Greece, about 350 BC. So this is around the same time as you have Euclid and his Elements. But whereas Euclid's Elements is really aimed at somebody with roughly a high school education, Archimedes' work is meant for mathematicians. Although this is certainly well within the realm of anybody in high school. If you look at some of the rest of his work, though, it ends up being a little bit more sophisticated. But let's go ahead and talk about it. Our goal is to, we're going to try to approximate pi. And what we're going to do is we're going to use a little bit of geometry where basically we take a circle, and you like that circle drawing skills? That's right, yeah. And we're going to have it with a radius 1. And then we know that the area of that circle is going to be, say, pi r squared, or just pi, because r is 1. So if we can get a good approximation of the area of the circle, then we go to good approximation of pi. And our first approximation is going to be made by putting a square on the outside. And this is obviously going to give us an upper bound. And we can get a lower bound by putting one on the inside. But since this is roughly the length of a radius, that means that the square has side length 2. So an upper bound on pi is 4, at least for the very beginning. And the lower bound we can get this way. So if we inscribe a square, then what happens is this length here is 1, and so then we have a 45, 45, 90 triangle, and that makes this square root of 2. So our lower bound is the square of that is 2. So just from the very beginning, we get a ballpark estimate of pi being between 2 and 4. And that's not bad. And if we take the average of these two guys, we can say that pi is roughly 3, say. So that's not bad. This is roughly the same sort of estimate that you would have in the Bible, where they're describing the fountain in Solomon's temple, and they say it is about 3 times round as it is across. So that's not bad. But we'd like to do better. So how would we do better? Well, let's go ahead and start shaving off bits of the square. So what I'm going to do is I'm basically going to take a tangent to the circle and chop off this bit. Zoop, zoop, and here, until I have a perfect octagon around the square, around the circle. And so again, the circle is inscribed in the octagon, and the area of the octagon will be an upper bound on the area of the circle. Okay, so now rather than doing anything by hand, let's just go ahead and see how we can show that this is actually going to converge. And we're going to use some calculus techniques, and this will hint at a lot of stuff that we're going to end up doing in our class. So first, what we're going to do is we're going to take each one of these triangles, and the idea is that we're going to double the triangles every single time. And by doubling the triangles, we're going to end up reducing the angle by half each time. So the first angle that we had for the square, mapping from here to here, was pi over 2, right? But now we're mapping, but now we reduce it, and now we're going to have pi over 4. And we know that the height of this isosceles triangle is 1. Because this is a point on the circle. So basically what we're going to have is, we'll just call AN is the area of the nth polygon. And so what we'd like to do is we'd like to be able to figure out an equation for AN. And so this is what we have. All right, so we know that's 1, and we know that basically AN is going to be equal to the base times the height divided by 2. And since height is 1, it's just base divided by 2. So we can use the fact that this is a right triangle and that we know this side length, and then this is going to be pi over 8. But let's be a little bit more general. Generally speaking, each time, since we're going to be dividing it by 2, we're going to have the full angle here is going to be pi over 2 to the n minus 1, and this little angle, the half one, is 2 to the n. Okay, so this angle here is 2 to the n, and so then we're left with this triangle here, and so we have pi over 2 to the n, and this is side length 1, and we have an opposite side, and so basically if we want to compute, figure out the area, we need twice of whatever this opposite side is. So then we have, let's choose yet another color. I like blue best. So AN is equal to 2 to the n times the area of this triangle, and the area of the triangle is going to be twice whatever the opposite side is, times 1, right? Okay, well, let's figure out what this opposite side is. If I just take tangent of pi over 2 to the n, then this is going to be opposite over 1, and so that's just opposite, right? So again, I get this, and so we have 2 to the n times, say, was it 2 times tangent of pi over 2 to the n? I feel like I made a mistake somewhere. Hold on, let me think. We need to divide that by 2. So, and this was the triangle, Tn triangle. I'm confusing area of the polygon with the area of the triangle. So let's say Tn. Let's see. All right, so this should have been divided by 2. This divided by 2, and then that's going to be 2 to the n times tangent of pi over 2 to the n. Sorry, I just had lunch and I'm starting to fade, so I apologize for those mistakes. But at the same time, this isn't going to necessarily be on the exam, so it's just sort of a fun chat about numerical analysis. Okay, so this is ultimately the areas that Archimedes was getting, and what I'd like to show you is that as n goes to infinity, it's actually going to converge to pi. So now we're going to start using something that is a little bit more calculus oriented, and so what we're going to, so we've established that the area is equal to 2 to the n times tangent of pi over 2 to the n. Now I want to show that this converges, so our claim is this converges to pi as n goes to infinity. All right, so why don't we go ahead and prove that? And the way we can prove it is we can use the Taylor series for tangent. So we know that tangent of x is equal to x plus x cubed divided by 3 plus x to the 5th over 5 or something, over something I can remember. You know what? And it doesn't even matter. This is what we'll generally call higher order terms. And so generally speaking, when you write this is going to fall under the category of what we're going to do called big O notation. And it's going to turn out that you can, in a lot of cases, just sort of paste all those guys in here. And generally what we know is that, we have x to the fifth, x to the seventh, x to the ninth, etc., all appearing in tangent. We know they're odd because tangent is an odd function, but otherwise this is what we get. So now let's go ahead and plug in these values. So we know that 2 to the n times tangent of pi over 2 to the n is going to be 2 to the n, that was too many parentheses, is going to be 2 to the n times pi over 2 to the n, going in for x. Then for x cubed, we have pi over 2 to the n cubed divided by 3, and plus higher order terms. And if I multiply by 2 to the n, what do I get? Well, 2 to the n cancels 2 to the n on that first term, and on the next term, we're going to get pi cubed on the top, and on the bottom, we're going to get 2 to the 3n on the bottom. And then those are going to cancel. It's going to leave us 2 to the 2n plus higher order terms. And so basically, it's just going to be bigger and bigger powers on 2 to the n. Well, as n goes to infinity, that goes to 0. So we'll just say as n goes to infinity, basically we have all of these terms going to 0. And in fact, if you want, we can even make it a little bit more explicit. 1 over 2 to the n here, and then we can have pi cubed over 2 to the n plus other terms. But this is sort of finite. And so as n goes to infinity, that's going to be going to 0 times some finite quantity. And so we have 2 to the n times tangent of pi over 2 to the n goes to pi. And there you go. So that is a proof that Archimedes' method works. So that was one of the earlier examples of doing numerical analysis and trying to compute digits of pi. There's still quite an industry around digits of pi, although it's gotten to be a bit ridiculous. I can look up real quick while we sit here. Digits of pi record. Let's see what that is. Yeah, so right now people know 31 trillion digits of pi, and that is a bit too much. I think this goes to Emma Haruka Iwao, I guess. And apparently she did it in combination with Google, and this was back in March of 2019. Before that, I think if we go back to the last person who did it by hand, I think that was, let me see. Last person to do it by hand. So Ramanujan came up with a good method at some point, and either the desk calculator, and this is 1949, so we're not talking like a digital calculator, but probably mechanical, was done by Levi Smith and John Wrench in 1949. And let's see, yeah, just trying to see if there's any big names that I know of. Ramanujan was a really big one, and his method was used for a long time. Ferguson, D.F. Ferguson, hit a lot of really big ones, but back then, that was in 1949. Smith and Wrench basically got to 1,120 digits, and so now we know over a trillion. By the way, in order to get to like a few centimeters accuracy of the circumference of the entire solar system, you need something like 10 digits, 12 digits, or something like that. But certainly it could be done with less than 100 digits of pi, and so going to trillions is a bit absurd. Anyway, but yeah, so that continues. But yeah, let's talk about the next thing on the list, and this is going to be Heron's method for square roots. Okay, so Heron's methods of square roots. This is about the 1st century BC, and this is in Egypt. So this was Hero of Alexandria, who came along and came up with this method. And the method is actually fairly straightforward. Basically, our goal is to find the square root of some number s, and basically we start with a guess x that we think it should be bigger than the square root of s. If x is bigger than the square root of s, then that means that s over x should be less than the square root of s. And then if we take their average, we should get probably something closer. So basically, so we average those two quantities, and this is what we get. So we say that the next guess, xn plus 1, should be equal to 1/2 of s over x plus x, n, the last guess. And so, and this is Heron's method. It is equivalent to Newton's method, and that you use with like polynomials like x squared minus, s, and that would give you exactly this formula. So we can go ahead and try to work this out. There is some apocryphal things I've seen that basically says this goes back to 17th century Babylonians, but I mean that's we don't have any actual evidence of that. We just know they have computed square roots. So so Heron gets the credit because that's what we have preserved. So what do we have? So let's go ahead and try finding, say, the square root of 2. So if we're trying to find the square root of 2, our first guess, x naught, should just be something bigger, and so we're going to guess 2. And so if I use 2 as my guess, then x1 should be 1/2 of, say, my last guess, or say 2 divided by the last guess, so 2 over 2 plus, say, 2. And so that's going to be the average of 1 and 2, I think. Yeah. And so that's going to give us 1.5. Okay, so that gives us a guess. Secretly, we know that root 2 should be equal to 1.414, and so let's see if we can get at least 2 significant digits. At least we're spitting distance at this point. X2 should then be 1/2 of, say, 2 divided by 3/2 plus 1.5. I converted a fraction just to help with arithmetic. So we get 4/3 plus 1.5, and 4/3 over here on the side should be equal to 1.333, etc. Right? So ultimately, this gives us 1.2 times 133 plus 1.5, and so we get 1/2 of 1.8, or sorry, 2.83 repeated. Right? Okay. Let's check my arithmetic. Yep, looks good. So let's go ahead and take that and have that. So that's going to be 1/2 sorry, 1/2 of that. This should give me 1.4, and I think 6666, etc. I think. Let me just ask Google. All right, so what is 2.8 divided by 2? And Google tells me it is 4.41666666. And 6. There we go. So we see we actually found the first 3 digits with Heron's formula with just 2 iterations. And Heron's formula is pretty quick at getting us to the right answer, and so with just 1 or 2 applications, we can probably figure out that at least the first 5 significant digits past the decimal. So that's really handy. All right, so following this up, historically speaking, let's talk about tables of logarithms and how you would come up with that sort of thing. I'm not going to do exactly what Briggs did. I just don't have the time. Not in a small lecture like this. Even to find one of those tables, it would probably take a day. At least to the accuracy that he did. But this is roughly what Briggs did. So logarithm tables. All right. So this is roughly Briggs' method. I'm not going to do it any justice, and maybe I'll make a video that really will dive into this later. But here I just want to give you sort of an idea of these things. So this is Briggs' method, and it was done by Henry Briggs back in 1561. Oh, well, he lived between 1561 and 1630. Okay. So then basically this is how we're going to try to do it. So you can try to say you want to find an entry on the table, and so you want to find log base 2. Now this is, when I write log here, I'm meaning log base 10. And so what Briggs did is he tried to find powers of 2 that were really close to powers of 10. So for instance, we know that 2 to the 10 is 1024, which is roughly 10 cubed. And so we can go ahead and do that. We can say, well, let's figure out what log 2 to the 10 is. And so we think that this should be roughly log of 10 cubed. And well, this is base 10, so that should be 3. On the other hand, we know that log 2 to the 10 should be equal to 10 times log base 2. And so if this is equal to 3, then that tells us that log base 2, or approximately 3, then we should say that log base 2 should be equal to roughly 0.3. And let me ask, oh, why is Google, what is log of 2? And Google tells me it is, log base 2 is roughly 0.30102, etc. So that's not actually a bad estimate right off the bat. And at the same, now Henry Briggs actually had methods for correcting, and maybe we'll talk about that later. But it sort of delved into sort of a proto version of calculus and Taylor series. And generally, how he made his tables, other than this, was to take a look at powers of 10. So, for instance, if we take a look at, say, log of 1,000, we just said this should be equal to 3. Now, you can descend through and come up with a whole lot of new values for your table by taking, say, square roots. If I take the square root of 1,000, then I get 1/2 of log base of 1,000, and so this should give me 3/2. But then I need to figure out what is this, and that's where Heron's formula comes in. So he would use something like Heron's formula to actually get a good estimate on this, and then he put that in his table, and so then he would ultimately have a decimal expression for the square root of 1,000 is equal to 3/2. And then he can get at other values that are maybe close by through averaging. And so then we can even take this up. We say, all right, well then let's say log of the 4th root of 1,000, and this gives us 3/4, and etc. So he'd just fill up his table with all these values, and then if there's something sort of in between, he could try interpolating. And that's something common we would do with that. Like I said, this is not precisely Heron Briggs method, but we can do another video that really dives into that later. Okay, now finally, I'd like to go ahead and talk about Fermat's method of quadrature. And this is pretty interesting. This is so Fermat himself. He lived from 1607 up to 1665, and AD, obviously. And this roughly predates Newton. So Newton, he was born in the 1640s, and calculus, Newton's calculus wasn't really invented until he was 21, and so that would have put calculus coming about roughly around the time of Fermat's death. And just the idea of this being disseminated throughout Europe, Fermat probably never saw the works of Newton. Although, you know, history can surprise you. So maybe he did actually see it. Who knows? But what you're going to see here is that Fermat actually came up with a way of integrating x to the n. And so let's go ahead and start that. So what we're going to be trying to do is we're going to compute the integral from 0 to a of x to the n dx. And so we're basically going to have the power function x to the n, and what we're going to do is we're going to, if your calculus 2 class went into it, you will know that you can actually chop up the interval into a whole bunch of rectangles. Usually it was the same width, and then you use this as, say, an estimate on what the actual interval is going to be. But what's significantly different about Fermat is he actually used a series of these rectangles underneath the curve. Rather than a fixed width, he actually let the width shrink, so you'd end up with an infinite number of these things. And so we're going to set an r between 0 and 1. And so this is going to give us a whole bunch of values, ar squared, ar cubed, ar to the 4th, etc. And we're basically going to get a lower bound on this integral. But the idea is that as r goes to 1, I don't know why I keep doing that. As r goes to 1, this should go to, these rectangles should go to filling out the entire area. So what we're going to do is we're going to come up with a formula for all these partial, for this sort of lower bound, and then we're going to have take the limit and show that it converges to what we expect. Now, since we've taken calculus, we know that this should go to a to the n plus 1 over n plus 1, so this is what we're looking for. Okay, so why don't we go ahead and take a look. So this is going to amount to figuring out exactly the areas of each of these squares. And so you need a base and you need a height. The height is easy enough. This is ar to the n. This one is going to be ar squared to the n. This one is going to be ar cubed to the n, etc. And this width is going to be a minus r. The next one is going to be ar minus ar squared, and etc. And so we can go ahead and put this together. And so, the area, which depends on r, is going to be a sum of, as m goes from 1 to infinity, and it's going to be ar to the m. Yes, ar to the m, raised to the nth power, times, we're going to have ar to the m minus 1 minus ar to the m, and that should be all those squares. But now the trick is to come up with a way of actually, figuring out what the sum is. And the idea is that we're going to use geometric series. Geometric series, that formula we've known how to compute since the Greeks. It was in Euclid's Elements. They had a nice geometric interpretation, a proof of the series converging, and it's one of the few cases where the Greeks actually comfortably took a limit. So this would have been known to Fermat, and so this is available to him. All right, so let's go ahead and simplify this so we can actually exploit it how we'd like. There's a lot of terms that we can pull out. So out of here, this becomes a to the n and r to the mn. The series depends on m, but not on n, so I can take n out. So we have a n there. This term becomes a times r to the m minus 1, and then this left over is 1 minus r. So I can take out another a, let's just put it to the n plus 1 here, and I can take out 1 minus r. And what it leaves us with is a sum from m equals 1 to infinity of, let's see, it's going to be r to the mn plus m minus 1. Yes. And that's basically this term and this term surviving. Okay, so that's good and all. If you take a look at this, it is going to be m to the hold on, just making sure we get everything right. Okay, so we can pull out one other thing, just for our convenience. So a to the n plus 1, I can pull out an r to the negative 1. So we have 1 minus r, and I'm pulling out 1 over r. So I guess m equals 1 to infinity of r to the m times n plus 1. There we go. Okay, so take this to the next page. And so we see then that we have this. So we have a sub r is equal to this. And I'm going to change the indexing. So a sub n plus 1, we have 1 minus r divided by r. And this leaves me with sum m equals 0 to infinity. So I'm shifting everything. Did I do something wrong here? I keep feeling like I did something wrong here. We'll see in a second. All right, so if I shift that around, oh, yeah, that's what I did. Okay, so I get r to the m minus r to the m plus 1 times n plus 1. All right, and this is why I was dumb. We can work this out real quick. So this is going to be mn plus m plus n plus 1. And I can get this guy back in there. Oh, that was dumb. All right, well, that's fine. It's not incorrect. 1 minus r, the sum, m equals 0 to infinity. And so now we're left with r to the mn plus m plus n, and then I can hack off that, that plus 1 by using the reciprocal there. And now I can pull out something else. So we have 1 minus r, and finally I can take out an r to the n, and this leaves me with an m equals 0 to infinity of r to the m times n plus 1. Yes. There we go. Okay. All right. Tedious, but nothing too complicated. So an plus 1 times 1 minus r, rn. Now I can use the geometric series formula. This is the same as writing r to the n plus 1 raised to the nth power. So this becomes 1 over 1 minus r to the n plus 1. And yeah, There we go. So now, what would we like to do? Well, the general idea, like I said before, was to let r go to 1. And if r goes to 1, this shrinks, and it should converge to value. If I take that limit, though, I basically have this. I'm going to have it a to the n plus 1 times r to the n of 1 minus r over 1 minus r to the n plus 1. Now, you could use Hopital's rule in our modern world, but remember, differential calculus hadn't been invented yet, and Hopital wrote his book after Newton, and his book was a first in calculus, although Hopital's rule is really due to John Bernoulli, if I remember correctly. But there were a bunch of people after Newton and his calculus. So all this wasn't available, but polynomial factorization was. And so if you take a look at 1 minus r to the n plus 1, you can actually rewrite this as 1 minus r times 1 plus r squared plus all the way up to rn. So this guy then can be written as a to the n plus 1 times r to the n times 1 minus r divided by 1 minus r times 1 plus r squared all the way up to rn. These terms cancel, and so what you're left with is a to the n plus 1 r to the n divided by 1 plus r plus all the way up to rn. Now, as r goes to 1, we have that this goes to a to the n plus 1 divided by 1 to all the way up to n. So this is 1, this is n terms, but yeah, the 0th term is going to get n plus 1, right? And there you go. So Fermat figured out how to take an integral of a power function, and since we know that you can basically take linear combinations underneath integrals, and you can split integrals over sums, and you can pull out scalars and differences and all these other good things. That means that Fermat actually came up with a method to integrate all polynomials. And so I don't think he actually framed it that way. I think he was happy with just being able to get this. But this is sort of a precursor to modern integration theory. So, yeah, I think that's all I was going to talk about today. Let's see, double check my list. Yeah, and so that's good. So yeah, so that gives you a general idea of some numerical analysis and so, or at least in history, and what people worked on it. And we're going to work on a lot of the similar problems that these people were working on, but using a little bit more sophisticated mathematical techniques. And specifically, we're going to use a lot of calculus. All right, so that's where I'm going to leave it. And yeah.
Hey, all right, so welcome back. Yeah, that's some basic numerical techniques that are historical. Now, for the rest of the class, we're going to be going into a little bit more detail on how to do everything, and basically what it means to be close to the quantities that you're looking for, and convergence rates and whatnot. So, anyway, I hope you enjoyed the lecture, and I'll see you next time.